So on to question 11 from chapter 3 of An Introduction to Statistical Learning. This video will be done in R, and I'll make a separate video for Python. Like I said, we're on question 11, and this is a multi-part question, A through F. And I've listed all of the questions here at the head of this collab sheet, but we'll tackle them one at a time as they come up. But before we do anything, we need to generate some fake data, and on that data we are going to do some stuff with regression. So this is the code block for generating that data. All right. So I have a variable here for x, an object here for x, which is just 100 randomly or normally distributed random values, and then y, which is another set of 100 different random numbers, plus 2 of whatever the number for x was, right? So x and y are linked by, so y on average is about twice as big as x plus some noise. There's also this command right here, which is called set.seed. So these random number generators here, or commands, they are generating numbers pseudo-randomly. And I say pseudo because they're not completely random. They go through a very complicated process, or not very complicated, but a process that spits out random numbers. And depending usually on the time of your computer, it's using that as a seed and then performing some mathematical operation on that. So instead we just set it to 1, so that every time you run this code you would get the same numbers. So if you set your seed to 1, you'll always you should get the same numbers that I do, unless somehow the software of R changes at the time that you watch this, in which case you may have slightly different number, or very different numbers. I don't know if they ever do that or not. But anyway, so we have x and y, and the first thing that we're going to do is we're going to perform simple linear regression without an intercept, and I'll show you how to do that, or it says so in the question. Well, let's do that. So here I have my regression for y onto x, and in order to remove the intercept, I put a 0 here. Okay, and that 0, so R normally assumes that you're going to use an intercept, and so by putting a 0 in my formula, I'm telling R don't use an intercept. Okay, so I'm going to run that, and I get my summary output, and that's not very relevant to us right now, but you'll notice that here there is no intercept term in the coefficients. If I were to remove that 0, I'll do it real quick. If I were to remove that 0, there is an intercept term. Okay, so anyway, put that back. All right, and now the next thing I'm going to do is, instead of regressing y onto x, I'm going to regress x. Make that look pretty. Regress x onto y. Again, oh, that should say without an intercept. Okay. Okay, so now I'm just doing the reverse, right? So now x is my outcome, y is my input variable without an intercept. Okay. And so again, we get these results here. We get the coefficient for y on x. But now we want to look at the relationship obtained between A and B. All right. Give me just 1 second. Okay. So we want to look at the relationship between A and B. And so when I go through here, so here I've just pulled out the this line and this line from my previous 2 equations, and you notice that we get different estimates. Okay. But the t value, as well as the p value, although I've rounded to 4 decimals, and it goes it's far less than 0, or far less than the numerical accuracy of 4 decimal places. But these are identical. Okay. Again, different estimates, but that makes sense because y is supposed to be about twice as big as x. Okay. So anyway, so there's a relationship between A and B, and I think that it has, what the question wants us to realize is that the t values are identical. Okay. Now in part B, we are meant to basically do an algebraic proof showing that t, the t statistic given here at the beginning of my proof here equals this guy right here. And so I'm not going to step through the proof, but of course you can look at the Colab sheet, or I guess pause your screen and go through the steps. And hopefully I haven't made an error in here. I got to the right answer, so presumably I have not made an error, but you should check it for yourself. But I just start with t, and I give the formula for t, and then I just start expanding terms, and pretty soon you get to the desired result. And so we see that t equals that guy right there. And now it also wants us to show this numerically, okay? So in other words, here I have the outcome, or at least the t-statistic from our first regression, all right? And then this term right here is just a way to write this term right here, but in R. And so when we run these two, we see that they are equivalent. Okay, so this is the t-value we got in both of the regressions above, and this is the formula that we came up with for t, and plugging in the appropriate values. Okay. So now part E wants us to argue that the result from part D, this whole thing, would be the same for the reverse regression if we regressed x onto y instead of y onto x. So rather than going through the whole proof, I think that the easiest thing to do is to just recognize that x and y are simply labels. And so as I go through every step, just imagine wherever you see an x, put a y, and wherever you see a y, put an x. And of course, you're just going to come out to the very same conclusion. Okay. And let's see. Okay, so final part F. So now we're going to regress with intercepts, okay? And we're going to regress y onto x and x onto y, and look to see if the t-statistics again match in the two regressions, okay? So I have two regressions here, okay? Y onto x and x onto y. Notice that I have not added 0. So we do have an intercept, and when I look at this is an ugly thing here, but I encourage you to break it down in the code yourself and find out that this is the t-statistic, and we see that the t-stats are identical for the two. Okay, that is it. Like I said, I will make a separate video for Python, and I will see you next time.